Okay, so we're going to start with, after the prep that we did, we're going to start with data mining with R. And this is the first video. And so I'll just announce what I'm going to cover here first. So this is basically what we're going to do. We're going to talk about data preprocessing. So this is just like you have to get the data ready to work on it. And that oftentimes can be the hardest part, actually. Exploratory data analysis, that's just when you sort of try and look at the data and maybe you try and find what kinds of information is in the data. Maybe you get some ideas by looking at this, and then you might want to try and form some kind of model or make some kind of predictions or something like that. So that's called exploratory data analysis. And then after you sort of decide on what you're trying to do, then you do it. That's the predictive model construction. So we're going to make some kind of model. So let's talk about the kind of data that we're going to be analyzing this time. This is taken from a book called Data Mining with R, Learning with Case Studies, and we're going to look at the first case study in that book, which is about algae. And we're going to look at the problem of predicting the frequency occurrence of several harmful algae in water samples. So you can see that we're going to try and build some kind of model that will enable us to predict this. So the particular problem may or may not be interesting, that is about algae, but the technique is certainly important here. But the problem of algae, the problem is that high concentrations of certain harmful algae in rivers constitute a serious ecological problem, and that has a strong impact not only on the river life forms but also on the water quality. So being able to monitor and perform an early forecast of algae, they're called algae blooms, is an essential part of improving the quality of rivers. So the idea is to collect from water samples collect algae in water samples, and this was done in several European rivers at different times during a period of approximately 1 year. And then for each water sample, different chemical properties were measured, as well as the frequency of occurrence of several harmful algae. Some other characteristics of the water collection process were also stored, such as the season of the year, and the river size, and the river speed. So these were other variables that are also going to be included, or at least are available for us. And we want to build a model that does not require biological analysis, but just chemical analysis. And that's because biological analysis is expensive, but chemical analysis is cheap. So we just want to be able to do a chemical analysis of the water and then predict something about the biological activity of the algae. And once this is done, then we can we have a cheap, inexpensive, and automated way of monitoring for harmful algae. And something else that we may like to do is to understand the factors that influence algae. Now this seems like maybe part of the same problem, but we want to distinguish between making a model that is predicting what's going to happen and then knowing the important components in what's going to happen. That's a little bit different. One is sort of understanding the factors. That's a little different than predicting what's going to happen, but we'd like to do both. So we want to know what are the important factors in algae growth. So the data for this study is available and was collected in the context of this And it's available from several sources, and this is a place you can look for data to use to do data mining, and the UCI Machine Learning Repository of Data Sets, and it's available there. And there are two main data sets for the problem, and the first consists of 200 water samples. And each observation contains information on 11 variables. 3 of these variables are nominal and describe the season of the year when the water samples to be aggregated were collected, as well as the size and speed of the river in question. The 8 remaining variables are values of different chemical parameters measured in the water samples forming the aggregation. So we're going to be looking at the data that we have is the pH value, the maximum, the minimum value of the oxygen, the mean value of the chloride, the mean value of the nitrates, the mean value of the ammonium, the mean of this, the mean total of that, and the mean chlorophyll. And the second data set contains information on 140 extra observations. And this is what we're going to use to test the model that we build. So this is the book's website, and we're going to go to the data sets and the algae blooms, and they provide in an R data format, which is they do some of the work for us here, but I'm going to just try and do it using the original data sets so that it's not so we're talking in general, not just how to use stuff from their book. So we want the analysis.txt file, but we may as well download all of these and store them in some directory on your hard disk, and preferably use the current working directory that you're running R from, this R session from. So I'm going to save it in my folder, which I've called Data Mining Algae. Oops. Let's see what it looks like here. There are no headers here. We can notice that, right? So these are variables, but we don't know what the titles, what the column headers are, what the names of the variables are. This should have the same set of, not the same, is it? Anyway, okay, and then this one. Okay. Okay, now let's try and read the data into R, into a variable in R. So first notice this is not a comma-separated file or comma-separated values. So we don't want to use the read.csv function. So I'm going to use a read table, and I have to put in the right location. So I want to get that location here and put it in here. And now recall that this won't work unless I put double slashes here. So I need to do that. So I put in double slashes, and now I'm just going to hit the return key, but this statement is not finished, so it's going to give me a plus sign. And now I'm going to tell it that there are no headers, and then I'm going to hit the enter key again. So I'm not finished yet, so I'm going to tell it that the decimal point, the decimal numbers are read with a dot, and then I'm going to tell it about the column names. So I'm going to say column.names equals, and then I'm going to give a vector with the column names. I'm going to tell it this, which means if you look in here, sometimes there's blanks, and I have to tell it what indicates a blank. So not available strings look like this. Okay, and now I close it with a second bracket so the end the statement. Let's see if this works. And it did work, much to my amazement. It works. So that means I've read algae into, or I read this data into the variable algae. Now let's see what it looks like. Let's do the head function on algae. This function, and we can now see that this is the data that we have, and it has given the columns the names that we specified. Just to reiterate, this NA strings indicates that there's a vector of strings that are to be interpreted as unknown values. And these values are represented internally in R by the value NA that is not available. Now, just to review, R has a lot of different ways to read in data. I just mentioned the read.csv was another one. I've shown in these videos that there's you can just use file choose to open up a file. Sometimes that is the easiest way, sometimes it's not. If you want to find information about this particular method, you can type $read.table, and it opens up this help function, help page for this function. And there's also a manual that comes with R that you should check out called R Data Import/Export. So we said that we're going to do data preprocessing, exploratory data analysis, and predictive model construction. And right now we want to do some visualization of the data and some summarization of it. It's always good to get some kind of summary and maybe some kind of picture of the data. So if you type this, we can get some summary statistics about the data. So what are we getting here? For example, the season, we get that there's autumn, spring, summer, and winter. And there are, I guess, 40 cases where the samples were taken in the autumn, 53 in the spring, and so on. I think we talked about the size of the river. It can be large, medium, and small. Now, you may have thought that the size of the river was a numeric variable, but they're treating it as a nominal variable, saying that it can take just the values large, medium, and small. And the 45 means that there were 45 cases where there were large rivers, and 84 that there were medium rivers, and 71 small, and so on. The speed is also going to be, in this case, they're treating it as a nominal variable. Just can only take on the values high, low, and medium. I guess this was the maximum pH level in the river was the minimum number was 5.6, and gives some other statistics here as well. This is the first quartile, the median, the mean, the third quartile, and the max. So, and then so on with these as well. Now, I'm not a chemist, I'm not a biologist, and to be honest, I don't really know much about these chemicals, but this is the data that we have. Now, we can also get some kind of picture of each of the variables if we like. For example, we can type in this command to get a histogram of the maximum pH from our data set. Let's try that. And so this is a histogram of the maximum pH. if you type in this command without the probability equals true or the prob equals t, you get the same shape, but the y-axis is now frequency, whereas if it was this one, it's probabilities. And you can switch from the graph to the console by doing that. So if you've studied some statistics, you would recognize that this distribution is fairly close to a normal curve. So we would note that the distribution of the algae pH level, maximum pH level, is close to normally distributed. Okay, and you could present this picture as part of your study, part of a report that you would make or a paper that you would write. If you want to get a less of a visual confirmation that it's normal and more of a numeric confirmation, you can use something called the QQ plot in a package that's available called the CAR package. And to install that, you have to go to Packages and Install Packages. First, it will ask you what mirror site you want to choose from. I already did that. So now I just choose the package. It's called CAR. And click OK, and hopefully it's there. So it's loading it. So now it's there. And now I can use that. And to use it, I can either go to, I think you can either do it, load the package there. Let's see if I do it that way. Yeah, it's there. You could do it that way. Or you could just do it this way, library car. So that just adds it. And then, so I said if we wanted to get a more visual representation, if you want to get a more numeric confirmation of the normal shape of this distribution, you can use something called the QQ. So let me try that. So first I'm going to run this command. This is about showing graphs. I said I want to get a numeric confirmation, but I'm also going to get a graph. And this says basically that I want to have two graphs in one screen. So basically I want to have two columns. So I'll just set that up now. So the first graph that I want is a histogram. And this is the data set that I want. I want probability. There's no X label. It's going to be blank. The main title is going to be this. And this, I think, tells that I want the y-axis to go from 0 to 1. So when I run that, I get this so far. Now I want to add in something else. The next thing is this thing. And this kind of tries to put a smooth curve on this distribution. So it's going to draw a line, and it's going to try to make what's called a density function or a probability function that fits this shape as well as it can. And I also and this is the data that we're using again, and this is that tells it to remove data that's NA, that's like the XXX values. So it doesn't have any problem with those. So now if I run this, I get this kind of smooth estimation of that distribution. And now I'm going to do this command here, and this basically just puts this down here, and this is just telling me where the actual data points were. So like this is what this axis is like 7. So there was something with an x, there was a piece of data with an x value of about 7 here, and about whatever this is, 6.8 here, and so on. So like there was nothing in between, say, 6.8 and 7. There was no data that had an algae maximum pH, say of 6.9 or something like that, but there was something down here, there was something up here, and there are all these others. And this jitter means in case there were sort of double values, it sort of spreads them out just a little bit so you can sort of see them, I guess. Okay, and this is rug, so it's kind of underneath. And now we're going to put on another plot, and we've already set up the sort of two columns here, so the next plot can fit on the same page. And we're going to be using the same data again. We're going to use this QQ plot, and the main is a normal, represent a line that represents a normal distribution, and we get this. So the solid line here is what, if it was perfectly normally distributed, all the data would be on this line. If it's not perfectly normally distributed, some of the data, or those little circles, will not be on the straight line. Now, these lines here, this dotted dashed line and this dashed line, are like we call it the 95% confidence interval. So if it was normal plus or minus something, we expect that there's some random error off of this normal line. So we don't really, even if the data is normal, we don't expect it to look normal because we're taking a random sample. So sometimes we'll be off the line, but these dashed lines say this is like a 95% confidence interval. So data that's outside of here would make us believe that perhaps it's not completely normal. So if a lot of the data is outside of here, it would suggest that it isn't normal. And it also isolates the data which falls outside of these 95% confidence intervals, and that can tell us, oh, well, like these points might be unusual in some way, and these points might be unusual in some way. In fact, these points are clearly unusual, or they clearly don't fit anywhere near a normal plot, is what I should say. So these points happen to be where the x coordinate is low, and so that means, of course, that the maximum pH was quite low. So those ones are, maybe we can notice these and kind of flag them and check them out. Maybe there's some error there. Same thing with these values over here. In fact, these are probably the same values. These are quite far away from most of the data. So these dots here can suggest that maybe the data is not normally distributed, or these can suggest that maybe these were data that were somehow recorded wrong, or there was something unusual about them, that they're not really part of the same kind of data that the other dots are from, and maybe we could even get rid of these dots. Or we could just say that the data wasn't normally distributed. Now, going back to our code here, you can see that we use function composition quite a bit here. And just to remind you what I mean by function composition, this is an example of function composition. F of g of x, we say that we're taking the function g and putting it into f. And that's happening a lot in our code as well. For example, we're taking here lines, and we're putting inside the lines function the density function. And these arguments here are arguments for the density function, not for the lines function. So whenever you have difficulty in understanding this type of instruction, you can always sort of look at them separately, one at a time, to fully understand what they're doing.